Let me move on to our next speaker, Professor Jun Chen. So are you ready?
Yes, I'm ready.
Okay, so please share your screen.
Sure.
Professor Jun Chen is a rising star, right?
Thank you, Yadu. Thank you for.
Yes, I'm ready. Okay, so he is the assistant professor, very young, then in the Department of Bioengineering at the University of California, Los Angeles. He has published 2 books and 250 journal articles, and Dr. Chen was identified to be one of the world's most influential researcher in the field of material science by the Wearable Science Group. And he is an associate editor of Biosensors and Bioelectronics. And he has been highly cited researcher from 2019 to 2020 in Web of Science. Please welcome Professor Jun Chen.
Okay. Yeah. Thank you very much, Yadu. Thank you for your always strong support and certainly great organization of this great event. Actually, to give a talk after Professor Kaimat gave me a lot of pressure. I enjoyed his wonderful work a lot. So today, actually, I would like to share with you a story entitled "Smart Text for Personal Health Care." So why we need a personal health care? So look at this curve. Actually, this curve is describe the relationship between the disease burden and also the cost. Look at our current health care system is based on typical intervention. What does it mean? Does it mean, for example, if you feel discomfort, if you have headache this morning, maybe you will just make a call to a doctor to make an appointment. So the doctor will check his schedule, said maybe the earliest available time is tomorrow afternoon. So you have to wait. So until tomorrow afternoon, then you drive a long distance to clinic center, get some treatment. So this is the version of the current story. So I have been thinking about if we could perform the earliest molecular detection, so the situation could be changed. So what does that mean? So for example, if I wake up this morning, I feel discomfort, I have a headache. So no. So if I have a body temperature sensor, which is keep reporting my body temperature, and this morning when I check my self-NTP, said, oh, my body temperature a little bit abnormally high, then I will report the data to the doctor over distance. I just text him or her or email or just phone call. So he or she will give me immediate care. Said, maybe Dr. Chen, as assistant professor, you have a lot of pressure or stress. Now it's time for you to slow down a little bit, drink some hot water, and take a good sleep. Maybe the headache will not come to me. So this is a concept of personal health care. So it's based on disease prevention rather than the current health care that's based on disease management. And also is based on the health enhancement. And certainly they will have a high quality and low cost. So high quality means we don't need to going through this kind of bad feeling of headache. And the low cost, actually, we don't need to visit the clinic center, get some treatment, eat some medicine. We just need to slow down a little bit, drink some hot water, and take some sleep. Then the headache will not come to us. So you can see definitely this type of concept of personal health care has a lot of advantage compared with the current health care based on typical intervention. To realize this type of health care transformation, I think one of the big challenges that is we have to develop wearable biomedical devices just like a temperature sensor, which could keep reporting our physiological information. If we find some abnormalities, we can report those to a doctor immediately to get some care or attention. So, but those wearable biomedical devices, because we need to continuously monitor, so those devices will wear against our human body for a long period of time. Certainly, wearing comfort is very important. Otherwise, people may feel reluctant to wear those type of devices. And also, the price could not be very high. If very high, maybe we cannot utilize it for daily usage. So to develop those type of wearable biomedical devices with wearing comfort and also the affordable price, actually a big challenge in that field to realize this type of health care transformation. So Apple Watch is one of the very famous devices which could keep reporting our heart rate. but it definitely has disadvantage. For example, is additional burden to wear, especially for our scientific researchers and student professors. Actually, we type a lot on a keyboard, so those watch definitely will give us inconvenience when we're typing on the keyboard, and also very expensive. So to solve this problem, I noticed that actually textile is indispensable component in our daily life, and everybody's supposed to wear clothes to go to work, otherwise the policeman will have a problem with you. And the textile has advantages, for example, the wearing comfort, and they have very good scalability to fabricate. For example, we can use weaving or knitting machine to construct those textiles. And also our human beings have a long history with textiles. Textiles serve a number of advantages to be developed into biomedical devices. First, it has a wide range of materials choice, from natural materials, for example, cell wool, cotton, to synthetic materials, peptide, polyimide, polyester. So all of those materials actually, many of them are biocompatible, biodegradable, and even bioabsorbable. So that's gives them a lot of advantage if you could develop them into bioelectronics or biomedical devices. But how to develop those devices into biomedical devices, into bioelectronics, that actually is another level of challenge, because look at those materials, they are chemically inert and they are not physically conductive. So it's very hard for you to develop into bioelectronics. So actually, I noticed that human body has a lot of biomechanical motions. For example, when I give a talk now, my mouth is moving up and down, my fingers bending, and I'm certainly breathing, and I have heart beatings. So I have been thinking about, can we use textile products to convert those biomechanical activities into electricity, use the above-mentioned materials to construct those type of biomedical devices. Once those textile components converted those biomechanical motion into electricity, we would harness those general electricity for either energy, sensing, and therapeutic applications. So very recently, the editor-in-chief of Nature Electronics invited me to write a review paper, just talking about smart textile personal health care. It's a very comprehensive review to present this concept. Here, due to a time limit, I just want to show you the first figure of this review. Actually, this figure is talking about the timeline platform technology development for smart healthcare textiles. So I think why the editor-in-chief invited me to write such a review, because my contribution to the smart healthcare textile is to contribute to platform technology into the community. One is Triboelectricity-based devices, another is Magnetoelasticity-based devices. So in the following slide, I will introduce you what is those two platform technologies. So the first one is Triboelectricity. So what's Triboelectricity? So actually is a phenomenon, how is the contact electrification phenomena. So what is contact electrification? So when we are very young, we're educated that when you use glass to friction itself using general static charges, you can use those general static charges to attract small items. Or in the cold winter, especially in the dry, in the northern part of the U.S. or northern part of Korea, also when it's very cold. So at that time, we take off sweaters. You can see sparkles in the darkness. All of those are because of contact electrification. So actually, in 2012, we just harnessed those phenomena to develop a fundamental new working platform, which is able to convert mechanical pressure into electricity. How that works? As watch the video. So here, so when there's two polymer layers, just like the blue and the purple one, they're dissimilar. So when there's mechanical force to bring the two contact with each other, just transfer interface, one will be electric charge, another will be positive charge. So those charges are static charge, as I mentioned previously. They can sustain on the surface a long period of time. So if there's biomechanical force to deform this polymer layers to induce a periodic contact separation cycles. So those that will generate electrical potential difference between the charge plane. So if we coat a thin layer of metal electrode on just like a yellow layer shows on the back of the two polymer layers, so this kind of periodic contact separation will drive electrons to flow back and forth in a pair of metal electrode. By doing this, we can generate alternating current in internal circuitry. So this technology certainly has a number of advantages. First, that is based on supercharging effect. So the polymer layer could be very thin. We can use just 20 micrometer thickness of the polymer layer. That's good enough. For the metal layer, as long as it's conductive, that's enough. That's 100 nanometer is good enough. So you can see the total thickness of this device could be controlled below 20 micrometer plus 20 micrometer, 40 micrometer, and plus 200 nanometers, because each of the metal layers is 100 nanometers. So you can see the total thickness of device could control below 50 micrometers. That is the diameter of human hair. So you can see this device could be very soft and also very efficient. Also is very efficiency. It's very easy to generate the voltage up to 100 volts. So actually, this platform technology invented in 2012, and after 10 years development, actually last year the pioneer Professor Jun Chen wrote a review paper to show the influence of the research scholar globally in this community, and I'm lucky to rank #2 right after Professor Jun Chen. So this is one platform technology. So another one is magnetoelasticity effect. So this platform technology we recently discovered in UCLA. So what's magnetoelasticity effect? So magnetoelasticity effect is the effect discovered in Italian scientist Valery, so we can call it Valery's effect as well. So in 1865, Valery discovered some metal alloy. So when they apply mechanical pressure to those materials, so they can induce a magnetic flux density change. So you can say when you apply mechanical pressure, the magnetic flux density of bulky material decrease. So when you release the force, so magnetoelastic effect, actually the magnetic flux density goes back to original state, but it requires mechanical pressure up to 20 megapascal. So actually the phenomenon here, the physical science behind this observation is that when you apply mechanical force, they will induce magnetic domain tilted inside the bulky materials, then they will induce a magnetic flux density decrease. So, but those effects only observed in rigid metal alloy in the past 150 years. So very recently at UCLA, our group discovered extended its effects to a soft polymer systems. So actually we just mix some polymers. We could use some biocompatible polymers as a polymer matrix, and then we just mix some magnetic nanoparticles. We show that when you apply mechanical pressure to those soft composites, it can also induce magnetic flux density decrease. But the required mechanical force is reduced from 20 megapascal to 300 kilopascal. So we just expand this effect to soft bioelectronics community. So we take the soft composite of the mechanical coupling layer. We put it we call it MC layer for short. So the MC layer is for the mechanical to magnetic conversion. So on the top of the MC layer, we just coat another sort of metal electrode with just a metal coil. Actually, we can, for example, we can use liquid metal, so which is actually very soft, to construct this magnetic induction layer. So once you apply mechanical force to those composites, induce magnetic field change. So the magnetic field change could be picked up by the magnetic induction layer to generate electricity in internal circuitry. So basically, the MI layer is for magnetic to electric conversion. So a combination of MI layer and MS layer, we can realize mechanical to electric conversion. But these devices have a good advantage that's intrinsic waterproof, because the magnetic field could penetrate the water molecular, not like the Triboelectricity I introduced previously, based on the contact education. So definitely humidity is a big killer to that platform technology. But this device is intrinsically biocompatible and also waterproof if we use some biocompatible polymers. So, and after the publication, after the publishing, the paper is selected from cover of the last December issue of Nature Materials and highlighted by Nature as well. So today's talk, I just wanted to show you how can we use those two platform technology to construct different type of textile devices for biomonitoring, therapeutic, and energy applications. So the first application scenario is biomonitoring. So the first application scenario I here want to show you is about sleeping quality evaluation. So sleeping disorder actually is a modern, is a major health threatening high-paced modern society. Actually, it would result in mood disturbance and many heart-related diseases. So maybe someday in the morning, when your partner wake up beside you and get mad at you, maybe it's not because you have bad personality. He or she has bad personality just because he or she is going through the sleeping disorder. So for the sleeping disorder evaluation, so far we have two platform technology. One is polysomnography. You can see we have you use a sleeping nap and then you have wells to wrap around the body for monitoring. Another one is cell phone APP. So during sleep, you just put a cell phone onto a bed sheet, and then when you move on the bed, then actually those kind of induced mechanical pressure could be detected by cell phone APP. So those two technologies certainly have disadvantages. For example, they have very complex structural design, and also they have high cost. And for the cell phone APP one, you can see that for iPhone is about $100, and if you want to use the APP, maybe it's additional $20. We can see it's very expensive and also inconvenient to use. So those you can see this polysomnography company. You can see this wells wrap around your body, maybe make your sleeping disorder worse. And also, it's not enough accuracy for them cell phone APP one. So for some of tiny pressure, they cannot be detected because the cell phone itself has a bulky structure. So to solve this problem, recently we developed our pressure-sensitive large-scale battery sheet. So this small battery actually very sensitive to the pressure. So certainly it could be large-scale fabricated. So but the smart batteries consist of a number of pressure ring. So each of the this kind of pressure sensor ring, actually each of the pressure sensor here actually is a Triboelectric sensor that I introduced previously where I used Triboelectricity to do that. So these are two close view of this three-layer structure. So on the top we have conductor fabric. In the middle we have a wave shield PET elastic membranes. So when there's biomechanical pressure applied onto this smart battery sheet, actually they will induce a contact change between the contact fabric and also the PET. They will generate a current or voltage in internal circuitry. So the device is very sensitive. We show that when you just use a finger to gently touch the battery sheet, you can see it can generate voltage up to 3 volts. So we can just analyze the frequency, the amplitude of generated electricity. We can monitor the sleeping behavior. Actually, you can see here, we just use the body movement and body movement to classify the sleeping into 4 situations. One is a awake state, wake sleep state, light sleep state, and a deep sleep state. Actually, we just use the generate amplitude or voltage signal and to classify those sleeping behavior. So you can see this monitoring is continuously from 11 p.m. That's the time you go to bed and wake up at 8 a.m. So it's a continual monitoring. So we can see that for this participant, actually at 2:30 a.m. in the morning, he or she has a time span 3 hours deep sleeping. That means this guy is very lucky and he or she doesn't have sleeping disorder. So for this type of three-layer structure, actually is very bulky and they cannot wash it. So, but for smart textiles, definitely you need some time to clean the textile for further usage. So the washability definitely is required. So very recently, we also developed another single-layer ultra-soft washable smart textile. So you can see the scale box 1 meter. The textiles could be large scale fabricated. Similarly, very similar to previous design, we still use this kind of soft fibers, functional fibers to construct different sensing unit. If I take close view one sensing unit, here actually we just insert this functional fibers, just like green fibers shown here, into the commercialized fabric. So those devices also very sensitive to the tiny pressure because the functional unit is tightly sealed in a second tube. Is what intrinsically actually it's not intrinsic waterproof, but it's waterproof. Actually, look at here. So if we put this piece of textile in a tank of water, if you apply mechanical pressure to the device, it can also generate voltage up to 0.8 volt. So we can use generate electric signal to do some biomonitoring purpose. So here the application scenario could be the sleep apnea. So what is sleep apnea? So somebody may stop breathing during the sleep. So if you cannot wake him or her up immediately, it may cause death. So here we just cover this textile on the belly part of the participant. So you can see when they breathe, the belly will up and down. They'll give a mechanical pressure to this small textile. We can generate voltage up to 1 volt, those regular peaks. So when he or she stops breath, you can see they will generate a large fluctuation in the output voltage signal. We just develop those fluctuation into a warning signal to trigger a phone call or to notify he or her family member over a distance to wake him or her up immediately, or otherwise it may cause death. So for sleeping monitoring, for this kind of respiration monitoring, we can not only use smart textile, this kind of battleship smart textile, we can also use facial mask as well, because COVID is outbreaking in the past 3 years. So facial mask become a requirement in our daily life. So I have been thinking about, can we engineer the facial mask to construct an unmasked sensor network for respiration monitoring? Here is our design. Basically, we just deploy 5 pressure sensor onto a facial mask. So when you breathe, so there are some fluid dynamic between the mouth, between the mouth and also your facial mask. Within these cavities, actually there are some fluid dynamics. So we can analyze those fluid dynamics actually to monitor our respiration behavior. So you can see that the 5 sensors corresponding to 5 channels of electrical signal output because they are working independently. So you can see that for when you breathe, each channel actually is generate electric signal independently and differently. So we just analyze generate electric signal and to use signal processing procedures going through some amplifier and filters and actually use machine learning algorithm. So with the result, actually we show that this type of device could monitor different type of respiration behavior. For example, when you normal breath, deep breath, when you cough, when you talk, when you have respiration failure, the detection accuracy could be as high as 100%. So in the future, it's a wear a piece of facial mask, and then you can monitor respiration behavior on your cell phone app. If you find some abnormalities, you can notify those to your doctor over distance immediately. So Textile could not only choose for this kind of respiration and also the sleeping related study, it certainly could apply for pulse wave monitor as well. So here is one of another design, which is starting with the functional fibers to mimic the human muscle fibers, use electron spinning to construct this kind of long woven textile. So we show that when you wear this piece of textile against your leg artery site, so you can see we can continuously convert your auto vibration into electricity. So we just calculate number of peaks divided by time and give us the heart rate. You can see before and after exercise, your heart rate increased from 73 per minute to 92 per minute. So this long movement textile actually lack of breathability. So very recently we fabricated a real fabric-based devices. We still take the silver-coated fabric as substrate, and on top of them, we just construct this kind of flower-shaped devices. Each flower shape is actually the flowers made of a lot of functional fibers. Each of the fibers actually I show here actually is a pressure sensor. It's very sensitive to the auto vibration. So look at the detailed structures designed with functional fibers. We just use 3 polyester yarns to twist the metal yarns. So here is a cross-section view of the functional fibers. So how does it work? So basically, when you wear this piece of device against your artery site, when your blood vessels compression expansion, so this tiny mechanical pressure can induce a contact area change between the polyester and the metal yarns. With the result, it can generate electricity in internal circuitry. So here is the experimental data. So when you wear this piece of textile against the west artery site, actually they are able to convert the artery vibration into a analog signal. Actually, this is a voltage signal up to 3 volts. You can see, let's take one close view of the one cardiac cycle signal. You can see that a lot of typical point, PS, P, and PD could be clearly read out. So those generate electric signal actually analog signal. If we wanted to readout by cell phone app, we still need to go through a number of single processing and transmission. Those analog signal we are going to filter, amplify, analog to digital converter, and finally we can use Bluetooth to timely display your pulse waves in a cell phone app. So in the future, it's a well piece of textiles, and then take out cell phone, they can read out the pulse wave profiles, and if you find some abnormalities, so you can report those data to doctor or participant immediately. So here is a video to visualize operation procedures. So basically, these are textile devices, and here is a circuitries for single process and transmission. Here is a wireless receiver to receive the general electric signal. Here is a continuous monitoring result or the pulse wave profile. So you can see those pulse wave profile could be continuously monitored. So actually, for those wearable bioelectronics which relies on energy conversion technology, they have a big challenge, that is a motion artifact, because those devices could not only convert auto vibration into electricity, they can also convert your arm bending or finger bending, those biomechanical motions into electricity as well. So in order to address those motion artifacts, so very recently we introduced machine learning to process the generated analog signals. So as a result, after the machine learning algorithm, we show that actually those devices is able to continuously monitor blood pressure even with this kind of arm bending, this kind of biomechanical motion. So we validate our result compared with the commercialized cardiovascular monitoring. You can see the result is very similar to each other. So in the future, it's one with a piece of devices, even you are doing exercise, they can control without the possible profile as well. So as I introduced at the beginning, so for those type of wearable bioelectronics, because they have either skin interface with skin, where it has a lot of perspiration. For implantable devices inside the human body, we definitely have a lot of biofluid. So that means for this on-body application, we have a lot where in a high humidity environment, those challenges definitely face a lot of challenge to the Triboelectricity enable wearable bioelectronics. So very recently, we discovered magnetoelastic effect in soft system for energy and healthcare. So you can see that this device is stretchable and soft and is all-in-one body design, and also is intrinsically waterproof, as I mentioned previously, because the magnetoelastic effect could penetrate the water molecule. And also we culture some human fibroblast cells on the device. You can see the cells live very well on the device. That means that the device has very good biocompatibility as well. So far we are pioneering this research work, this research effort in the world, and with about 10 papers published so far, and certainly ACS Nano give me a lot of support, and really appreciate that. Yeah. So the first application scenario I want to share with you, that is pulse wave monitoring devices. So certainly we just made short fibers with magnetoelasticity, and then we just wave those devices with some conductive yarns. With the result, even underwater situations, those textiles able to convert pulse wave into electricity. And here is a profile generated even with perspiration or underwater situation. You can see this electric signal generated in one contact cycles. You can definitely be very sensitive to read out all of the rich information in the pulse wave vibration. And the devices has very good biocompatibility as well. So we just measure the cell viability on the device compared with the control group. You can see these devices, MEG devices, actually is very biocompatible. So in the future, even you have lots of perspiration on the skin, so this doesn't show electric impact on the measurement result of your cardiovascular profiles. So these devices also apply for respiration monitoring as well. So even also with heavy perspiration situations, you can see when we wear these devices against the chest areas, you can see during the normal breath, rapid breath, they generate different waveform of electricity. So you can see we just analyze the general electrical profiles, so we can realize the self-powered this kind of respiration monitoring. So this device could also be extended to human-machine interface area. So here is one of our design. So basically, you can say devices is intrinsically waterproof. So even you have heavy perspiration on your skin, so it doesn't show negative impact on its performance. While showing that we can use those control panel to wireless control this music player. So when they play the song, pause, or play next song and the last song, you can see definitely we can wireless control this music player. And this device certainly is foldable and rollable and intrinsically waterproof. And actually, we also trying to extend its effect to customer implantable device as well. This is our first research actually to develop implantable magnetoelastic devices. So in order to increase the biocompatibility of a device, because the magnetic particle may be toxic to the tissues, in this work we just coated a single layer of silica onto the magnetic particle to make the device more biocompatible. Not only have biocompatible magnetic nanoparticle, but also have biocompatible polymers. So we're showing that when you attach the devices to a rat, you can see when a heart beating, you can see they can generate electricity accordingly to mirror the diastole and systole of the cardiovascular informations. And we also extend this effect to the wind energy harvesting community. So this recent work we published on the advanced materials. So basically, you can see that because usually in nature, the rain is accompanied with wind. But if you wanted to harvest the wind energy, the device should be waterproof. So that's actually the advantage of our device. We're showing that when we use a wind turbine to deform this kind of devices and to induce magnetic field change, we're showing that even with water, if we just spray some water on a device, you can see they can generate a current up to 10 milliamperes. Actually, in the field of biomechanical energy harvesting, 10 milliamperes actually means a lot. So, and also you can see we can use those generate electricity to sustainably perform the water splitting. You can see we can use those generate electricity as a direct power source to the water splitting. You can see basically a lot of bubble generated. So this is one of the wind energy harvesting. And this work actually, the postdoc Dr. Oak actually contributed a lot. Dr. Oak graduated from KAIST with a PhD degree, and he's doing an outstanding job in my group right now. So Dr. Oak actually also applied this effect to harvest water flow energy as well. So to fully utilize the intrinsic waterproof advantage of this technology, we show that when you use a wind turbine to deform two MEG devices, you can see they can generate voltage up to 3 volt, current up to 20 microamperes. 20 microamperes actually very high. So, but compared with current voltage relatively low, so we can also to make this output power useful. So we use a transformer. After transformer, we can show that the current could be up to 3 milliamperes, voltage could up to 20 volts. So definitely this electric stimulator could be a very useful power source to have some small electronics or to do to promote some chemical reaction, just like water splitting, as I showed previously. So that is the part about the biomonitoring. So the second section is therapeutics. So we can also use textile therapeutic devices. So due to the time limits here, I just give one example. That's assistive physical therapy. Actually, 37.5 million Americans 18 and older report trouble hearing, and actually 75% of them are in an unemployed state. So because the lack of effective communication tools, if you don't understand American Sign Language or sign language, other sign language, definitely is very hard to communicate with them. So to solve this problem, recently we developed a glove. Actually, it has to perform this kind of wearable sound-to-speech translation. So the glove has two components. One is stretchable sensor unit, which is able to convert this kind of finger-spelling biomechanical motion into electricity. Another is a wireless flexible PCB printed circuit board for single process and transmission. So we're showing that when wireless power gloves and perform standard American Sign Language to express letters ABC, numbers 1 to 3, or short phrase, for example, I love you. So basically, you can see those generate electricity from 5 fingers. So we just use generate electricity recognition patterns. We can realize this kind of sound-to-speech translation. So here is a video I would like to share with you to visualize operation procedures. So certainly by programming, we can set this translation language into Korean, into Chinese, Spanish, or many other language type. So this work actually, after reported, is covered by more than 200 million coverage in the world. And also, especially NPR gave me individual interview. And also this work also highlighted by Science as well, is put as a top 10 science story of 2020 by the OSC, this kind of is the science center. And also the Arithmetic is a big database tracking the record of the publications. So the Arithmetic put this article up as the top 100 among 3.4 million work published in 2020 across all of the subjects. So that is one story about therapeutics. Last one is the energy. So people may think why energy is a portion of personal health care. So look at this future wearable biomedical devices. You can see here is a wearable circuitry for biosensing. Here is a wearable ultrasonic sensor for cardiovascular monitoring. So there's certainly the power to drive them. So this is beyond the capability of current battery system. Look at those batteries. They have rigid structure and they have a bulky structure, and also they're made of toxic element, and they will release heat during the discharging. So that will make, if you wanted to apply for skin interface device or implantable devices, those generate heat may make you feel discomfort. To solve this problem, we still going back to textiles. So when you wear clothes, go to work, certainly we have renewable energy source available. One is solar radiation, secondly, mechanical deformation. So here is one of the solutions we apply to harvest energy simultaneously from solar radiation and mechanical deformation. So this hybrid textile has two components. One is triboelectric textile is able to convert biomechanical force into electricity. Here is another solar textile made of dye-sensitized solar cell. We use fiber shaped dye-sensitized solar cell and use weaving technology to construct this piece of solar textile. So the experimental result shows that with the size of 4 centimeters by 5 centimeters, just like half of adult palm size. So under one sun condition, this device is able to deliver a stable power supply more than 0.4 milliwatt at a wide loading resistance from 1,000 ohm to 1 mega ohm. So with this actually energy harvesting capability, so those devices will demonstrate to harvest energy from sunshine and also biomechanical motions and to directly charge your cell phone. And also you can see with this small piece of textiles, and when you wave your hands under sunshine, this electronic watch could be sustainably driven. Energy harvesting textile is not limited to harvest energy from biomechanical motion and solar radiation. Actually, we can also use we use textile harvest energy for body heat or biochemicals. We can use textile thermoelectric generator or textile biofuel cells. So that Professor Joseph Wang here actually is leading research in the world to develop different type of fuel cells for biochemical sensor and energy application. Very impressive work. So actually, this actually is a invited review by Chemical Review 2,000 years ago. So we just in this review we just systematically summarize all of the energy harvesting textiles. So this review is entitled Smart Textile for Electricity Generation. It has a reference up to 800. So if you guys are interested in this concept or in this research field, please read this review paper. So energy harvesting textile, they have a disadvantages because the energy in nature actually is very unstable. So for example, when you wear a solar textile, walk in the shadow of a tree, so there's no sunshine available, so the output will be largely reduced. But for small electronics, you always need stable power supply. To solve this problem, we still need to borrow the capability, the regulation capability of fiber batteries. So recently, we developed a fiber-based solid-state zinc-ion fiber batteries. So you can see the device is actually very thin, just has a diameter of 120 micrometers. So we show that this fiber battery actually very stable. Even you bend the device or even you soak the device in the water, is always have very stable power supply. So this work recently highlighted us from cover of science advances. actually, we took a first step to hybridize the energy harvesting device and actually energy storage devices. Here's one example. So we just hybridize fabric solar cells with the fabric batteries. You can see that with sunshine, so the fabric solar cell is able to generate electricity. So those electricity could be sustainably stored in the fabric batteries. So at the discharge plateau of the fabric battery is always have stable power supply, no matter you twist your fabric or you work in the shade of a tree or even your raining days. So basically, as summarized here, with the regulating capability of fabric batteries, this photo-rechargeable fabric could work on a sustainable, stable power source for wearable biomedical devices. So let's go to a summary outlook of my talk today. Basically, our lab is trying to develop new platform technology using novel materials and novel structural designs to design different type of textile devices. They have capability of energy harvesting, biomonitoring, or therapeutics. So my vision to this field could be that in the future we can integrate those different text components into a piece of garment. So then some of the sensor, some of the text component could be power supply. Some of the component could be used for biomonitoring. Some of them could utilize for therapeutics to form this kind of closed loop sensor and therapeutic system. So 2 months ago, actually, Chemical Review invited me to write another review paper exactly entitled Electronics Textile for Wearable Quantum Care System. So if you guys interested in this concept, please read this paper as well. And actually, this paper, I showed that in the future, maybe we just wear certain type, if you have certain type of disease, we just wear certain type of clothes, then your disease can get treated. So let's come to the technology part of my talk today. So I would like to thank my wearable bioelectronics group at UCLA, includes a number of postdocs, PhD students, and also a number of undergraduates. Actually, I can say that UCLA undergraduate has very high quality. For example, the author actually now is a PhD student at Stanford. He published more than 20 papers together with me when he was an undergraduate at UCLA. And also, I would like to thank a number of collaborator contributors, including a number of professors from UCLA, Caltech, Stanford, and also funding agencies. So one last thing that I wanted to make an advertisement because KAIST is very top prestigious research platform in the world. So recently we launched our MedX is a new journal with Springer Nature. Actually, this is an international journal that's published breakthrough papers in all areas of biomedical engineering. So you can see here's all of the topics. So welcome you to submit high quality manuscript to this journal. And actually the editor-in-chief of this journal is very ambitious. So they are trying to make this journal compatible with Nature Biomedical Engineering. So, but it's just very young, very new journal. So please support the journal with your high quality manuscripts. So, okay, thank you very much for your attention. And here's the last figure to show the location of UCLA. You can see this UCLA campus, and it's a downtown LA area. So basically, it's about just 30 minutes driving distance. So welcome you guys to UCLA, and thank you very much for your time and attention. And I'm open to take any question if you have.
Thank you very much for impressive and beautiful presentation, Professor Jun Chen. Then we have several questions. So also you can refer the Q&A. So let me read the first question. I'm Hyunwoo Moon from KAIST. Thank you for your presentation. I have a question for soft electromagnetic system. In your presentation, you showed the MI layer was fabricated to patch style. Then I wonder how can you connect the biomedical sensor? Is there any special circuit like the triboelectric nano generator?
Yes, so definitely very much the working principle is generally similar to the Triboelectric nano generator. They are converting the biomechanical pressure into electricity. We just use those general electricity for analysis and to do the biomonitoring. So certainly we have to use needle wells to connect to read out general electric signals. So you asked me how can you connect the biomedical sensors? So definitely we need the needle wells to read out general electricity. Yeah.
Okay, the next one is you suggest two kinds of energy harvest for bioelectronics, including soft electromagnetic effect and triboelectricity. I think these two types of energy harvesters are similar with converting the mechanical energy to electrical energy. Then in the case of energy efficiency, what is the suitable energy harvesters for future bioelectronics in your perspective?
So this is also a very great question. So first, this is a magnetoelastic effect, not elastomagnetic effect. So yeah, so but as I said, we just discovered this effect last September, actually last November. Actually, is very new. So we are trying to extend this effect to different community to introduce the effect to the different communities. So far, for energy harvesting, we just apply them for wind energy or water flow energy harvesting. So generally, compared with those two energy conversion technology, Triboelectricity energy, they have very high voltage output, very low current output, and a very high inner impedance. But our device, magnetoelastic effect, actually, Triboelectricity is also my device as well. Yes, this kind of make me feel discomfort to say so. Yeah. So the magnetoelastic effect actually, because they have different working mechanism, so they have very high current output, very low voltage output, and actually very low inner impedance. So you can say those two technologies are actually is not like one is a win over another one. I think that they are just complementary to each other. Yeah. So for the energy conversion efficiency so far, because for energy harvest, this is a very new field. So far, we didn't quantify the energy conversion efficiency at the current moment, but certainly in the following several months, we will do that to quantify the energy conversion efficiency. Yeah. I hope I answered your question. Yeah.
Okay, thank you. Then next one is thank you for the great seminar. As is well known, the TENG output performance is negatively affected by temperature and humidity of the environment. I wonder how to control the external environmental factor to use TENG as an actual sensor. Also, what is the most significant difference between the TENG and MEG?
Okay, yeah. So first, for the TNG, as I said, is based on quantification. So it's a surface charging effect. That means you have to create a very dry environment for these triboelectric layers. Otherwise, the quantification will not happen. So that means to control external environmental factor, I think probably you can construct some waterproof layers. Actually, just like a surface of lotus leaf actually is super hydrophobic. So this is one strategy. Second strategy, very regular one, probably you can just add additional encapsulation layer to prevent the water molecule to into the triboelectric layers. That's could another strategy. So far, actually, in the community, people just mostly use those two strategies to do that. So your second question, that's the most significant difference between TNG and MEG. So certainly the working mechanism is totally different. We are using different physical science behind those two platform technology. So for the output on the side of the TNG, very easy to give very high voltage output and low current. Usually the current could be several microamperes. The voltage easy to be up to 100 volt. The impedance actually, inner impedance is as to several mega ohms. So, but for MEG, so the current easily to get several tens of microamperes. So the voltage actually just several millivolt or several volt. But the inner impedance actually just 10 to 100 volt based on our observation so far. So you can say those two technologies actually they have different physical science behind them, and also they have different output properties. So yes, so yeah, that's my answer to you. Yeah.
Okay, the last question, and I think this is related with the cost. So thank you, Professor Chen, for your exciting talk. In terms of commercialization of wearable e-textile technology, how easy would it be to integrate the different components for targeted application while also keeping the cost low?
Yes, so definitely if we want to commercialize the product, actually the cost definitely is it becomes a major concern. So I think here, so people actually, especially in Europe, a lot of companies actually are devote the effort to commercializing the smart textiles. So, or you can call it electronics textiles. So I think the big challenge in that is so far you can say, if you wanted to endow some functionality to the fibers, so you have to do some chemical coatings, especially on the polymer substrate. If you coating a layer of metal, so the adhesion between the two may be very weak. But if you wanted to use a Wearable knitting machine to construct such devices, so definitely we have a basic requirement or mechanical strength of the fibers. Sometimes, so for some of what I present here, we can only use hand weaving. We cannot use real weaving machines because those fibers, functional fibers with chemical coatings, is not durable enough to go through the weaving knitting machines. I think this is actually the big challenge in the community for commercialization. Yeah, I hope I answered your question. Yeah, in a general way. Yeah.
Okay, so thank you very much again, Professor Jun Chen, and